In early 1942, requirements for extreme armor expanded. German ordnance offices issued new breakthrough specifications. Hitler demanded immunity against Soviet anti-tank guns. The concept favored a terrestrial assault fortress. Initial mass targets exceeded 100 tons. Design authority moved toward Porsche leadership. Krupp received main armament and turret tasks. Alket received whole assembly responsibility discussions. Wohl Proof 6, coordinate procurement and testing. Documentation used the designation Panzerkampfwagen 8. The project name Maus entered internal correspondence. Weight allowances rose after each protection revision. Armor thickness requests escalated without mobility accounting. Planners assumed short-range operational employment. Staff papers described limited maneuver requirements. Engineering teams still needed practical drivetrain solutions. Porsche favored an electric transmission architecture. This choice aimed to reduce mechanical gearbox stress. Electric drive required large generators and motors. Generator mass added immediately to weight totals. Cooling systems enlarged to protect electrical components. Cable routing demanded additional armored conduits. The hull structure required deep longitudinal girders. Plate joints used interlocking stepped weld preparations. Weld sequences were specified to reduce distortion. Quality control demanded radiographic inspection procedures. Thick plate welding required multiple pass deposition. Preheating regimes were mandated for crack prevention. Post-weld stress relief remained difficult in field. Manufacturing relied on controlled shop environments. The hull used rolled armor plate segments. Front glacis thickness reached approximately 200 millimeters. Side armor thickness approached 180 millimeters. Rear plates were reduced to conserve weight. Roof armor remained thinner for structural practicality. Floor armor was increased against mines and blasts. Internal bulkheads compartmentalized crew and power systems. Turret armor became the most massive single component. Turret front thickness exceeded 200 millimeters. Turret sides remained near 200 millimeters. Turret roof thickness stayed far lower than faces. The turret ring diameter expanded for gun clearance. Large bearings required precise machining tolerances. Krupp produced ring components using heavy lathes. Transport of machined rings strained rail capacity. Factory cranes required upgraded load certification. Load tests used calibrated weights and safety factors. Turret casting was rejected due to size. Rolled plate fabrication became the feasible method. Plate bending used hydraulic presses with staged operations. Curved sections still required fitted weld seams. Weld bevels were machined to exact angles. Dimensional checks used large templates and gauges. On surface hardness specifications controlled ballistic performance. Heat treatment capacity limited throughput immediately. Armor plate suppliers prioritized other vehicle programs. Allocation disputes developed between Tiger and Maus. Minutes show repeated scheduling conflicts with Panther orders. Krupp requested relaxed delivery penalties in memoranda. The Ordnance Office issued revised milestone dates. New dates slipped after material shortfalls persisted. As design changes forced new drawings and part numbers. Revisions created obsolescence for already machined parts. Procurement forms tracked scrap and rework costs. Accounting entries show rising unit labor hours. Miles required parts beyond existing depot stocks. Standardization with other tanks was minimal. This increased the burden on spare parts. It also complicated training for maintenance units. Crew configuration required multiple specialized operators. About driver position remained in the hull front. Radio operator duties overlapped with auxiliary tasks. Turret crew included commander, gunner, and loaders. A second gun required additional loading procedures. The main gun selected was 12.8 centimeters. Designation aligned with KWK 44L/55 patterns. A coaxial 7.5 centimeter gun accompanied it. The secondary gun resembled KWK 44L/36.5. Ammunition stowage demanded large internal volume. 128 millimeter rounds were long and heavy. Handling required robust racks and restraining clips. Racks were designed to prevent shock detonation. Separate propellant charges complicated storage layouts. 75mm ammunition required additional rack space. Stowage planning reduced room for fuel. Fuel capacity became a constant operational constraint. The intended engine initially was Daimler-Benz MB509. MB509 was adapted from aircraft lineage. Later considerations included the MB517 diesel. Integration studies assessed torque curves and cooling. Engine bays were redesigned for alternate mount points. Mounting brackets used thick, gusseted structures. These structures added more kilograms to totals. Cooling airflow calculations required large intake louvers. Louvers became ballistic weak points in analysis. Designers compensated with angled covers and baffles. These covers restricted airflow and raised temperatures. Fan drives needed high power draw allowances. Radiators increased in surface area significantly. Coolant volume rose and added more weight. Exhaust routing demanded insulated passages near crew. Heat shielding used layered steel and asbestos materials. Maintenance access panels were small relative to systems. This increased service time for routine repairs. Electric transmission used a generator coupled to engine. Generator output fed traction motors near final drives. Motor housings required protection from mud ingress. Seals were specified, but remained vulnerable to grit. Electrical insulation had to survive shock vibration. Testing plans included extended running at load. The system needed precise voltage regulation controls. Controllers required complex switchgear assemblies. Switchgear occupied valuable protected internal volume. Power cables required thick copper conductors. Copper supply was strained by wartime priorities. Substitution discussions included aluminum conductors options. Aluminum required larger cross-sections for same current. That increased routing space and clamp counts. Clamps were standardized, but required many fasteners. Fasteners had to be high-strength alloys. Alloy availability was constrained by other armaments. Mild suspension used torsion bars and bogies. Road wheels were large to spread loads. Wheel discs were heavy and steel-intensive. Rubber tire usage was limited or reduced. This increased noise and vibration during travel. Track lengths were extremely wide for ground pressure. Width exceeded typical German heavy tank practice. Each link required precise casting or forging. Heat treatment ensured wear resistance of pins. Pin retention methods had to resist shear loads. Track tensioning required strong idler mounting points. Idler arms used thick plate and heavy bearings. Bearing lubrication schedules were complex and frequent. Grease consumption projections were unusually high. Track mass created problems during field replacement. A recovery vehicle could not easily assist. Existing Bergepanther capability was insufficient by calculations. Special recovery concepts were proposed but not built. Workshops would need cranes or gantries. Field units lacked such lifting equipment normally. Vehicle dimensions exceeded many transport envelopes. Overall length approached 10 meters range. Overall width exceeded 3.5 meters. Overall height approached 3.5 meters. These dimensions limited road and rail options. Rail transport required specially reinforced flat cars. Loading required careful weight distribution across axles. German rail limits constrained allowable axle loads. Bridge approaches at yards needed reinforcement works. Route surveys became mandatory for any movement. Surveys required engineer units and mapping staff. Each route survey generated detailed risk registers. Risk registers highlighted bridge collapse probabilities. Many bridges were rated far below mouse weight. Pontoon bridging could not support such mass. Standard assault bridges had lower capacity classes. Engineers proposed multi-bay support schemes. Those schemes consumed time and material heavily. Temporary trestle bridges were considered in papers. Trestles required stable banks and deep piling. Enemy artillery would disrupt such lengthy construction. Even peacetime construction would be demanding. Urban crossings posed severe clearance and strength issues. Road surfaces were not designed for 180 tons. Subgrade failure would immobilize the vehicle quickly. Turning stresses would tear pavement and culverts. Traffic control would be needed on any route. Movement would block roads for extended periods. Civil authorities would face evacuation and repair tasks. Fuel consumption predictions were unfavorable from start. Consumption rose with idling and slow travel. Engine efficiency was poor at low speeds. Electric transmission losses converted fuel into heat. Heat rejection required constant fan operation. Fan load reduced available traction power. Operational range projections fell to tens of kilometers. Supply columns would need constant refueling missions. Fuel trucks could not approach under fire safely. A single mouse would drain fuel allocations quickly. Germany already faced fuel shortages by 1944. Synthetic fuel output declined under bombing pressure. Allocation committees prioritized Air Force and submarines. Heavy armor fuel allotments were frequently reduced. Mao's planning ignored these macro constraints repeatedly. Mobility studies assumed slow advance with support. However, front conditions demanded rapid redeployment. Strategic mobility was essential on collapsing fronts. Maus could not redeploy without rail movement. Rail movement required intact rails and bridges. The Allied air interdiction reduced rail reliability. Rail yards were frequent bombing targets. Even unloading under threat was problematic. The turret required careful alignment during transport. Elevation locks were needed to secure guns. Lock failures could damage trunnions and bearings. Bearing replacement would require heavy shop tools. Turret traverse motors were electrical and complex. Traverse speed would be slow due to inertia. Stopping distance for traverse would be long. Gun stabilization was not fielded to modern standards. Firing accuracy depended on halting completely. Recoil forces from 128 millimeters were substantial. Recoil buffers required careful hydraulic maintenance. Leaks could render the weapon unsafe. Spare seals were specialized and not common. Barrel life required monitoring of erosion. Erosion measurement used gauges and inspection schedules. Replacement barrels were heavy and scarce. Barrel transport required dedicated handling equipment. Ammunition resupply required large cranes or teams. 128 millimeter shells weighed far more than 88 millimeters. Crew fatigue would increase reload time under stress. Rate of fire estimates were modest. Stowage limitations further reduced sustained fire. Fire control optics were planned but constrained. Optic supply faced glass shortages and bombing. Zeiss production disruptions affected many programs. Periscope and sight deliveries were inconsistent. Optical alignment in a huge turret was sensitive. Vibration could shift mounts and degrade accuracy. Calibration procedures required trained technicians. Such technicians were in short supply late war. The project moved from paper to prototypes. 2 hulls were ordered for initial evaluation. The first hull was designated V1. The second hull was designated V2. Turret production lagged behind hull completion schedules. V1 received a ballast turret or dummy mass. Ballast simulated turret weight and center of gravity. This allowed chassis and drivetrain testing sooner. V2 was intended to receive a complete turret. Final assembly occurred at selected facilities. Böblingen is associated with Porsche testing operations. Kummersdorf was a primary German test range. Test plans included road runs and obstacle trials. Obstacle trials required prepared pits and ramps. Ground deformation was measured during passes. Track sinkage data influenced ground pressure assessments. Whilst ground pressure remained high despite wide tracks, soft soils would still cause immobilization. Recovery from bogging was nearly impossible. Winching capacity of other vehicles was inadequate. Multiple vehicles could not coordinate safe towing. Towing points required reinforcement and were heavy. Even if towed, track damage was likely. Track pin shear risk rose during recovery attempts. Electrical components risked shorting underwater exposure. Engine intake height offered limited fording depth. Deep fording would flood compartments and motors. Sealing a 180-ton hull was difficult. Hatches and vision ports were numerous leak paths. Bilge pumps were limited in capacity. Pumps also required electrical power availability. Battery capacity was constrained by mass and space. Battery access required removal of panels and seats. Charging relied on generator output and regulators. Regulator failure could overcharge and damage batteries. Overcharge could cause gas buildup in compartments. Ventilation was necessary to prevent ignition risk. Ventilation itself created openings and vulnerabilities. Testing revealed overheating under sustained operation. Cooling adjustments required changing duct geometries. Duct changes required new plates and welding. Welded revisions were time-consuming to certify. Documentation demanded updated drawings and signatures. Signature chains created administrative delays. Each change required WWII 6 approval. Approval cycles took weeks under wartime strain. Meanwhile, factories waited for release to proceed. Idle time reduced efficiency and increased unit costs. Reports noted steering response limitations at low speed. Electric drive allowed differential torque, but with lag. Lag made precise maneuvering harder in tight spaces. Tight spaces were common in forests and villages. Turning radius remained large due to length. As pivot turns would churn ground and risk bogging. Churned ground increased resistance and fuel use. Slope climbing was limited by power to weight. Even modest grades could stall progress. Stalling under fire would be catastrophic tactically. Clutchless electric drive still depended on engine. If engine stalled, mobility ceased immediately. Restart procedures required time and stable conditions. Starter systems had to crank large displacement engines. Starter wear increased due to repeated attempts. Electrical faults could prevent any restart. Field troubleshooting would be extremely difficult. Spare parts lists were long and specialized. Toolkits would exceed normal tank unit sets. Maintenance manuals would be bulky and complex. Training programs would require weeks or months. By 1944, training time was sharply reduced. Crew quality declined due to attrition. Complex systems became liabilities in such conditions. As armor effectiveness was impressive on paper. However, armor alone did not create combat value. The mouse could survive certain direct hits, yet indirect factors dominated operational survivability. Air attack vulnerability increased with immobility. Allied fighter bombers targeted roads and vehicles. A massive silhouette was easy to identify. Camouflage nets were insufficient against aerial observation. Movement was slow, enabling repeated strike passes. Roof armor was thinner than frontal plates. Top attack munitions would exploit that weakness. Bomb blasts could damage tracks and suspension. Track damage would immobilize the vehicle fully. Spare track links were heavy and limited. Repair under air threat would be implausible. Artillery could register on a static target. Repeated near misses could damage optics and antennas. Shock could loosen internal electrical connections. Electrical intermittents are difficult to diagnose quickly. Engine deck fires were plausible under bombardment. Fire suppression systems were limited and heavy. Extinguishers required crew access during emergencies. Crew evacuation under fire would be hazardous. Hatch sizes were constrained by armor thickness. Turret hatches were heavy and slow to open. A disabled turret could trap crew inside. Turret traverse failure could block hatch alignment. Escape routes were therefore unreliable in failures. Logistics planners evaluated rail and road constraints. They noted axle loads beyond standard bridges. They also noted road width limitations. Village streets could not accommodate the turning radius. Trees and poles would need clearing operations. Clearing would reveal intent and consume time. Engineer detachments would be tied to one vehicle. This reduced overall operational flexibility for formations. Fuel supply units would need dedicated routes. Those routes required protection and coordination. House commanders would have to plan around mouse limitations. Such planning conflicted with fluid battlefield reality. The vehicle's speed was low in trials. Maximum road speed remained roughly in teens. Cross-country speed was lower than that. Even if it reached an objective, delays were severe. Delays allowed defenders to reposition anti-tank assets. Miles' main gun still required target acquisition time. Slow traverse reduced engagement rate against multiple threats. Close defense relied on escort infantry and tanks. Escort units would move faster and outpace it. Coordination would be difficult under combat stress. Radio communication suffered from interference in heavy armor. Antenna mounting required external exposure. External antennas were vulnerable to damage. Internal intercom wiring was extensive and failure-prone. Noise inside was high from fans and motors. Hearing protection affected communication clarity. Sub-periscopes provided limited situational awareness. High armor walls reduced visibility angles. Urban combat would be especially hazardous. Side shots at close range become easier. Even thick side armor has vulnerable points. Vision, slits, and joints remain weak areas. Track and suspension hits remain disabling. A disabled mouse becomes a stationary bunker. Stationary bunkers require stable supply and defense. Late war Germany lacked such stable conditions. Procurement friction increased as war situation worsened. Officials questioned value relative to multiple smaller tanks. Cost comparisons showed poor exchange ratios. Materials could produce several Panthers per mouse. Factory time could produce other weapons urgently. Yet leadership continued to push wonder projects. This reflected strategic denial in procurement culture. Hitler's preferences influenced acceptance decisions strongly. Engineering objections were noted but often ignored. Technical memos warned about bridge impossibilities. Those warnings were filed without cancellation authority. Budgeting continued through special allocations. Manufacturers complied to secure contracts and protection. Subcontractors delivered components despite skepticism. Inspection teams struggled to visit all sites. Transport of components faced bombing disruptions. Late deliveries forced rescheduling of assembly lines. Assembly lines were not optimized for such size. Jigs and fixtures had to be custom built. Fixture steel consumption was non-trivial. Cranes required reinforcement of shop floors. Floor loading calculations prompted structural retrofits. Retrofits delayed other production activities. Testing required dedicated ranges and security. Security was necessary due to secrecy directives. Secrecy limited distribution of manuals and drawings. Limited distribution increased mistakes and misassemblies. Misassemblies created rework cycles and delays. As rework required additional inspection and paperwork. Paperwork increased administrative burden late war. The mouse also faced ammunition logistics constraints. 128mm ammunition was not standard tank supply. It overlapped with some anti-tank gun calibers. However, packaging and transport differed. Tank ammunition required different stowage containers. Supply depots would need segregated handling rules. Handling rules reduced throughput under frontline pressure. Rail deliveries of ammunition faced air interdiction. Trucks delivering such rounds would be limited. Each mouse would consume heavy rounds quickly in combat. Resupply under fire would be unrealistic. The 75mm coaxial gun aimed at lighter targets, yet it required separate ammunition allocation too. Dual caliber supply increases planning complexity. Planning complexity increases errors and shortages. In combat, shortages translate to reduced effectiveness. Mobility constraints also limited tactical positioning. A tank must reach firing points reliably. Mouse would struggle to reach ridgelines. Soft embankments could collapse under its mass. Culverts would fail beneath repeated passes. Road shoulders would not support detours. Detours often involve weak ground near roads. Weak ground would trap the vehicle quickly. Bridge laying alternatives were considered on paper. No practical bridge layer could match its weight. Engineers suggested underwater crossings in some studies. Underwater crossing required snorkels and sealing. Sealing such a large hull was problematic. Snorkels would reveal position and require preparation. Preparation time would expose the unit to fire. River currents could push and yaw the hull. Yaw could jam tracks against riverbed obstacles. If stuck underwater, recovery is impossible. Thus, river crossing concepts remain theoretical. Testing did include limited obstacle water exposure. Results indicated significant risk to electrical components. Moisture ingress affected insulation resistance values. Low resistance causes shorts and thermal events. Thermal events can ignite oils and insulation. Fire risk within armored compartments is severe. Firefighting inside is hindered by smoke and heat. Ventilation fans could spread smoke to crew spaces. Gas masks would be needed for continued operation. Gas masks reduce visibility and communication. Operational efficiency would degrade rapidly. Even routine servicing posed large burdens. Oil changes required large volumes and containers. Oil supply already faced wartime rationing. Filter elements were specialized and could be scarce. Motor brushes and commutators required inspection. Brush wear would be accelerated by heavy loads. Commutator damage would require machining not available forward. Spare motors would be extremely heavy. Replacing a motor would require heavy lifting gear. Such gear would not be organic to units. Depot-level maintenance would be the only option. Depot maintenance implies withdrawing from combat zones. Withdrawal logistics would again face transport limitations. In late 1944, strategic retreat was continuous. Continuous retreat is negated depot maintenance practicality. Therefore, any major breakdown would be terminal. Terminal breakdown means the vehicle becomes scrap. Scrap denial required demolition charges planning. Demolition planning required dedicated explosives and teams. Explosives teams would need access under threat. If charges failed, capture would be possible. Capture risk drove additional secrecy measures. Secrecy measures further reduced field documentation. Reduced documentation increased maintenance errors again. By 1945, only prototypes existed. Series production had not begun in volume. Factories prioritized emergency repairs and simpler weapons. The Mao's prototypes saw limited movement under collapse. Reports indicate attempts to avoid enemy capture. Scuttling procedures were likely implemented to deny assets. Soviet forces later examined captured remains. Post-war assessments emphasized logistical impossibility. Analysts noted mismatch between protection and utility. The Mao's demonstrated industrial capacity, but poor prioritization. It consumed scarce materials for marginal battlefield impact. Its design reflected bureaucratic momentum over feasibility. It became a technical artifact of procurement failure. The vehicle's extreme weight dictated every limitation. Bridges, fuel, rail, and recovery were decisive. Armor and gunpowder could not offset constraints. The Mao's project ended as prototypes only. It remained unusable for sustained combat operations.